Okay, welcome back. This is the second part of the lecture about radiation and transfer of energy through the Earth's atmosphere, which will have consequences for things like the production of power on a solar array or something like that. We're going to talk about radiation real quick here in terms of waves in the electromagnetic field. And honestly, by the time you've reached a course like this, I'm sure you know about what radiation is and about how the defining property of any particular of radiation is going to be its wavelength, and how there's lots of different types of radiation depending on the wavelength of the radiation that is moving through the electromagnetic field. Whether we're talking very shortwave types of radiation like X-rays or ultraviolet radiation or even visible light, or longer wave type radiation like infrared or microwave or radio waves. Really the only difference between all these different types of radiation is their wavelength. I mean, even within the spectrum of visible light, it's a narrow range of wavelengths of radiation, and different wavelengths of radiation within that band, within that range, are representing different colors, or are interpreted by your eye and your brain anyway as different colors. So there's lots of different types of radiation out there, but they're all really just different wavelengths of waves in the electromagnetic field around us. And we can summarize the different kinds of radiation that the different objects around us are emitting. Everything around us emits radiation. That's part of what it means to be matter. We can summarize these with two main radiation laws. One is the StefanBoltzmann Law. And StefanBoltzmann's law says that the amount of radiation that an object is emitting at any given time depends on its temperature. The sun is very hot. It's emitting a lot of radiation. You are, approximately 300 Kelvin or something like that. You are emitting a certain amount of radiation. A cloud, which might be more like 250 Kelvin, is emitting less radiation, and so on. Hotter objects emit more radiation. Cooler objects emit less radiation. This is StefanBoltzmann's law. We don't need to quantify that law at the present time, but the idea that the amount of radiation that an object is giving off, being related to its temperature, is going to be important. The other important law is Wiens Law. Wiens Law is the one that tells us that the type of radiation or the wavelength of radiation that the object is emitting also depends on its temperature, with hotter objects mostly emitting shortwave radiation and cooler objects mostly emitting longwave radiation. The sun is extremely hot. The sun is mostly emitting at a very short wavelength that happens to correspond to part of the visible spectrum. It's a very short wavelength of radiation. It emits radiation at other wavelengths too, but the peak of it, where it's emitting the most, is in the visibles part of the spectrum. Cooler objects, like, say, you, are also emitting radiation, not as much per square meter as the sun is, but you are also emitting radiation, but Wiens' law tells us that it is mostly in the form of long-wave radiation, things like infrared and microwave radiation. So the two laws here are going to be telling us that there are going to be two types of radiation. I mean, we can kind of lump these ideas together and tell us that there's going to be shortwave radiation moving through the Earth's atmosphere, and this is going to be primarily from the sun. The sun emits a lot of it, and it's mostly at very short wavelengths. The Earth, it doesn't really emit any shortwave radiation like sunlight, and, like visible light or something like that, or ultraviolet radiation or anything like that. The Earth is at a much cooler temperature. It's going to be principally emitting long-wave or terrestrial radiation. Infrared radiation, microwave radiation, stuff like that. So at any given place in the atmosphere, you can measure radiation moving through the atmosphere. If it's shortwave radiation, it's probably from the sun. Maybe it is radiation that is transferring from the sun down through the atmosphere. Maybe it's radiation that reflected off the ground and is now headed back up through the atmosphere, but it came from the sun. Long-wave radiation in the Earth's atmosphere is emitted by things that are terrestrial, things that are at roughly the temperatures of like day-to-day life. So if you measure that there's some long-wave radiation transferring energy through the Earth's atmosphere, you are talking principally about things like radiation that's being emitted by the ground, or by greenhouse gases in the Earth's atmosphere, or by clouds, for example. Clouds emit at long-wave radiation wavelengths. Everything in the universe emits radiation. It is part, as I said, of what it means to be matter. Emitting radiation takes energy. The object that is doing the emitting of radiation cools down as it creates these waves in the electromagnetic field. So, for example, at night, the ground is emitting long-wave radiation and therefore cooling. The Earth's surface is emitting radiation upward into the Earth's atmosphere, which is cooling the surface of the Earth, as anybody who's, ever slept outside while camping could attest. On the other hand, absorbing radiation is picking up the energy on the other end. It is absorbing the radiation and increasing the temperature of the object that is doing the absorbing. That could be a greenhouse gas in the Earth's atmosphere that is absorbing long-wave radiation, or that could be the ground that is absorbing the solar radiation coming from the sun. A classic example here, you see these school kids here frying an egg on the ground, right? The ground is absorbing radiation from the sun and getting very hot enough to cook an egg in that particular case. In fact, when radiation hits an object like the ground, or a cloud, or an air molecule, or an ozone molecule, or your solar collector, or the roof of a building that's poorly insulated, or whatever, when it hits an object, when radiation hits an object, there's actually 4 different things that can happen. The radiation can be absorbed by the object, it could be reflected by the object, it could be transmitted through the object, or it could be scattered. We'll talk about each of those phenomena in just a little bit here. Absorbed is kind of the easiest one to think about. When radiation is absorbed by an object, as I've said before, it makes the object warm up. This could be like food in a microwave oven. The magnetron in a microwave oven produces waves in the electromagnetic field that happen to be at microwave wavelengths, and as it happens, food, in particular the water in the food, is really good at absorbing that kind of radiation. So the water inside of the food absorbs the microwave radiation and gets hotter, and then by conduction the water heats up the rest of the stuff inside of in your food. We could be talking about pavement. Pavement absorbs solar radiation really well and gets hot during the day. These are good examples of absorbing radiation. You want your solar panels to absorb shortwave radiation from the sun so that they can, then that can be produced into electrical power. Another thing that can happen to radiation when it is incident upon an object, or when it hits an object, is it can be reflected. Reflected means that the object is sending the radiation back more or less in the direction from which it came. Like a mirror. A mirror reflects the type of radiation that we call visible light. Down there on the ground there's a kid making a snow angel in that picture here. Okay, the kid is playing in the snow. When visible light hits the snow, it is mostly being reflected upward, up into the sky. That is a reflection of solar radiation. The thing about reflection is it doesn't change the temperature of the object that is doing the reflecting. The mirror doesn't get hot when you look into it because it's reflecting light. The snow is not warming up because the sunlight is reflecting off of it. Reflecting the radiation does not change the temperature of the object that is doing the reflecting. In fact, there's a related idea that's going to be important to us later in the semester, and this is an important vocabulary word, albedo. Albedo is the fraction of the shortwave radiation that is being reflected by an object. It's a number between 0 and 1, where 1 means it's reflecting all the shortwave radiation, and 0 means it is reflecting none of the radiation. So like if you wanted to talk about the albedo of a roof, okay, if the albedo of the roof was high, like let's say 0.9, that means that the roof is almost white. It is reflecting almost all of the radiation that is incident upon the roof, and therefore, the temperature of the roof might not be changing all that much. On the other hand, if the roof was very dark, maybe its albedo is 0.2. That means only 20% of the radiation from the sun, the solar radiation, is being reflected off of the roof. The rest of it is, either being absorbed or scattered or transmitted. We'll have to decide. But either way, it's probably absorbing a lot of radiation. So this can be an important factor of determining, for example, you've seen school buses that have those white roofs on the top. They do that because to reduce the albedo of the school bus. They want the school bus's roof to mostly reflect solar radiation rather than absorb it, because then the kids aren't complaining inside the bus so much that it's hot. And you can see that there's a wide range there of different albedos that I'm just providing for you here. Another thing that can happen with radiation when it's incident on an object is it can be transmitted. Transmitted can be a tricky word because we use it wrong in our day-to-day life. We talk about your cell phone transmits a signal or something. Transmits doesn't mean that. Transmit means the radiation goes through an object. Solar radiation is largely transmitted by air. By and large, solar radiation travels through the air rather than being absorbed or reflected or anything like that by it. The solar radiation mostly makes it through the air to your eye or your sensor or your solar cell or whatever you're using. I have an X-ray there. I showed a picture of an X-ray. When the dentist takes an x-ray of your teeth, the tooth material is your softer tissues are transmitting the radiation. The radiation goes through your tissues to expose the film on the other side, whereas like the tooth is mostly absorbing the radiation or scattering it, and the radiation does not make it through there. Your cell phone. The radio waves from the cellular tower transmit through the walls of your house. Your house is transparent to the radiation, and so as a consequence, when your cell phone is on and you're sending a signal, it can go through the walls there. The walls transmit the solar radiation. The radio radiation from your cell phone's antenna. Finally, scattered. Scattered is the final thing that can happen when radiation hits an object, and that doesn't have a whole lot of application to electrical load and yield. Scattering is kind of like, let me just real quick here, with the transmission, when radiation is transmitted through a material, that does not change the temperature of the material either. Air does not warm up when light travels through the air. Transmitting radiation does not change the temperature of the object that is doing the transmitting. Scattering. Scattering is kind of like reflection, but it is, instead of the radiation reflecting off the object and heading back in the general direction from which it came, scattering sends it off in a new direction. Scattering doesn't have a lot of application in electrical load and yield. Scattering is why it's hard to see oncoming headlights on a foggy day. Scattering is why the sky is blue during the day and red at sunset and sunrise. Scattering will have some applications later in the semester when we're talking about diffuse radiation from the sky. Even if the sun is behind a cloud, you still have light down here, and your solar cells can be measuring the light or converting it to electrical power. That's diffuse radiation that has been scattered by the clouds that you're observing. But we won't get to that for a long time. Scattering is certainly the least important with regard to the processes of electrical load and yield for what can happen when radiation hits an object. Now, before we move on to the third part of the lecture, I want you to consider another question here. Question 2. Part of the reason why it stays cold in the winter is that the ground is covered with white snow, which has a high albedo and blank radiation from the sun. And you have 4 choices there. Transmits shortwave, reflects shortwave, transmits longwave, or reflects longwave. So look through those choices and make your selection. Then follow one of the answers from below this video, and you'll get some feedback before you move on to part 3 of this lecture.